So again, welcome everybody to the first edition of the Zoom Geometry Model Theory Seminar. It's nice to see a few new faces that we don't usually see. The seminar is quite old in some sense. It first started over 20 years ago when there was a confluence of two programs at the Fields Institute, one in model theory and one in real analytic geometry. And it just happened that way, and we started to work together, especially between Bierstone and people like Van den Dries and so on. And since then, we have been running this seminar on and off, sometimes more busier, sometimes less busy. It was a little calm last year due to all the events, but hopefully we'll pick it up again this year. And it will certainly be busy again in 2 years if everything goes well, because we have another Fields program coming up in the winter of 2022. Anyway, without saying more now, I would like to introduce the speaker, Shaviv from Princeton University. He's our first speaker today, and he will speak on, as you can see on your screen already, Schwartz spaces of definable manifolds and Schwartz equivalence of planar domains.
Okay, thank you, Patrick. So can everyone hear me?
It's a bit quiet right now.
Yeah, great. Okay. Oh, it's too quiet. Yeah, I have no idea what I should do. So I will just try to speak up. Is it better?
Yeah, it's better.
Okay, okay. So thank you, Patrick, for inviting me here. And I want to talk today about two different but related subjects. So we'll talk about Schwartz spaces, or spaces of Schwartz functions, in two different frameworks. So the first will be the definable framework. We'll talk about this in the first half of this talk, and the second will be the quasi-conformal geometry framework. So the second half of this talk will be based on a joint work with Ed and Prives. Okay, so let's start. So let's start with what are Schwartz functions. So the setting will be quite simple throughout this talk. So we'll have an open subset of Rn. Later we'll talk about the complex plane, but we'll think about R2. So Schwartz functions for us will always be real valued. Even when we'll say Schwartz functions on the complex plane, we'll just think of Schwartz functions on R2. So what are Schwartz functions? So let's start with Schwartz functions on Rn. So these are should be thought of as functions that rapidly decay with an older derivatives also rapidly decay. So these are C-infinity smooth functions such that for any two multi-indices, so the alpha multi-index should be thought of the derivative multi-index of our f, and the k should be thought of the polynomial multi-index. So when we write x to the k, we mean x1 to the k1 times x2 to the k2 and so on. So if we take any polynomial and any derivative of f, and we look at this product, this should be bounded on the entire Rn, which means that f decays at infinity faster than 1 over polynomial for any polynomial, and also all the derivatives of f have the same property. So these are Schwartz functions on Rn, and Schwartz functions on our open set U will be Schwartz functions on the big space on Rn, such that for any point outside our set, we need to think about it as for any point outside our set, the Taylor series of our f at this point is identically 0, which is to say for any point and any partial derivative of f, the value of the partial derivative at this point z is 0. So this will be the space of Schwartz functions on U, and this will be the basic object we will study today. So let's say some easy remarks. So first, the Schwartz space of Rn is a Frechet space. There you have the topology. It's just the semi-norms given by these supremums. So we have countably many semi-norms, and these define the topology. Oh, you can see when I'm doing it. And S of U, the Schwarz space of U, is a closed subspace, and so also a Frechet space. The second remark, which is also quite important, we usually think of Schwarz functions on U as smooth real-valued functions on U. So in the definition, it is giving as a subset of Schwarz functions on Rn, but in fact, we think about functions that live only on U, and if we extend them by 0 to functions on Rn, we get this the same definition. So this is the same thing. And the third comment would be that if we take an open subset of an open subset, then extension by 0 gives us a closed embedding. And in fact, this is according to the second remark. So in the definition, you can just see that if something is a Schwarz space, is a Schwarz function on a small subset, it contains more condition than being a Schwarz function on the big space V. So we have this tower, right? So we have extension operator. And this is important because later when we will talk about sheaves, Schwarz functions will not form a sheaf, it will form a co-sheaf, which is the same thing with all arrows flipped, right? So usually we think about, I don't know, smooth functions, they form a sheaf. So it means that we have a smooth function on a big space. If we restrict it to an open subset of this big space, we get a smooth function. In this case, it's wrong. The direction is the other way around. So this is a pre-co-sheaf, and later it will become a sheaf. So there's your first proposition that will be very useful, especially in the second part of the talk, but it already makes sense to state it. So if we take a Schwarz function on the big space on Rn, that is identically 0 outside our set U, then there you have two equivalent conditions. The first will be that our function is Schwarz on U, which is to say that the Taylor series is identically 0 at any point outside U. And the second is that we have these bounds. So if we take our function f and we divide it by the distance to the boundary function, and even if we take the distance to the boundary and take any high power of it to the 10 or 15 or 1 million, and if we look at this quantity, it will be finite. So our f rapidly decays as it approaches the boundary. I want to stress that 1 and 2, as they are written now, they are not equivalent. We must also assume that our function f extends to at least a C infinity function or to a Schwarz function on the big space on Rn, right? Because you can have a function that satisfies 2 that goes to 0 really, really fast, but under this going to 0 really, really fast, it also oscillates even faster. So this will not extend to a C infinity function. But given that our function comes as a restriction of a function on Rn, everything is okay. So this is the proposition, we will use it later. Now, what is Schwarz equivalence? So two subsets of Rn are Schwarz equivalent if we can find a diffeomorphism between them, a C infinity diffeomorphism, such that it pulls and push the Schwarz spaces of the corresponding sets to form an isomorphism or Frechet space. Right, so if we have a function on V, we can pull it via phi or push it via phi minus 1 or wherever you put the stars and get a new function on U. So if this thing induces an isomorphism of Frechet spaces, we say that these two sets are Schwarz equivalent. So this is the definition. Now note that not any C infinity diffeomorphism induces such an isomorphism, right? So let's see an example. So if we look at the exponential map from the real line to the positive ray, this does not induce an isomorphism. Why? Because we have this picture. So please look at the right-hand side of this picture. So if we take any function on the real line that is 0 from some point small enough, so we don't care about the negative side, And for big x's, it decays like e to the minus x. So many such C infinity function exist. And of course, any such function is a Schwartz function of R. So if we take this function and we pull it via log or push it via exponent or whatever, if we first take the logarithm, meaning go to the coordinate system on the left, and then we evaluate our function, we get 1 over x for big x's, right? So on the left-hand side, this will not be a Schwartz function because it doesn't decay rapidly enough. So, the exponent map does not induce an isomorphism. Note, however, that the real line is Schwartz equivalent to the positive ray because we have another phi we can take. We have this x plus square root x squared plus 1. And you can check and see that this is a C infinity diffeomorphism that induces an isomorphism of the Schwartz spaces. Okay, so good. So these two subsets, the real line and the positive ray, are Schwartz equivalent, but not via exponent only, but for instance via this phi. Note that this phi is semi-algebraic, right? So it's a, or if you want, it's a definable function over R in the structure given by just the real line. And this leads us to the following proposition, and I will talk about this proposition with some detail, and later I will give many results without details. So there is the proposition: if we have a phi that is a diffeomorphism that is definable in some polynomially bounded or minimal structure, then this phi always induces an isomorphism of Roche spaces. So this is the proposition that I want to kind of almost prove, and later talk about other stuff. So maybe it's a good time to stop and ask if there are any questions, because we finished with the introduction, real introduction. Everything is clear? Okay, very well. And if you have questions later, please stop me. Good. So how to see this proposition is true? First, it's not a big surprise, right? It's kind of, you expect it to be true, but let's see how to prove it. So let's start by defining tempered functions. So tempered functions on, again, U, an open subset of Rn. The function is tempered if it satisfies two conditions. So first, if we take any alpha, a multi-index, which is, again, any partial derivative of our function t, and if we take any point outside our set U, then we can find the neighborhood of this point such that, and we can find some big, maybe very big integer m, such that if we look at the alpha derivative of t and multiply it by the distance function to the boundary, to the power m, so m may be very big, then around this neighborhood, around this point in this neighborhood, this quantity should be bounded. So how you should think about it? You should think about it that you should think about a function that maybe explodes as goes to infinity as you approach the boundary, but not too fast. Namely, we can find some polynomial in the distance to the boundary, some m, some monomial, it's the same, such that if we multiply these things, it will be bounded. So it doesn't explode like exponent as it approaches the boundary. And so this will be the first condition. The second condition will be the same condition, but for infinity. So for any multi-index of t, we can find, again, some monomial such that for big enough x, which is to say in the neighborhood of infinity, the alpha derivative of t is bounded by this monomial. Okay, so you can think of 2 as being the property of being tempered at infinity. Okay, so these are tempered functions. Now let's state, okay, so the space of all tempered functions is denoted by T of U. So now let's state 3 lemmas and see how these lemmas, I'm reminding you, we want to prove a proposition saying that definable diffeomorphisms in all minimal structures always induce Schwartz equivalence. So the first lemma will be the following. So if we take any function defined on U, then this function is tempered if and only if it has the property that if we multiply it by a Schwartz function, by any Schwartz function, we again get a Schwartz function. Now, one side is almost obvious, right? So if your function is tempered, then if you multiply it by a Schwartz function, you can immediately see that it is Schwartz. But the other side is also true, that if your function is not tempered, you can find the Schwartz function that if you multiply the two, you get something that is not Schwartz anymore, which is, again, not a big surprise, but you have to cook this function. The second lemma would be a very, I don't know, basic, or you can think about it as basic or as very technical. So if we have open subset and we take any map that pulls the Schwartz space of V into the Schwartz space of U, then the map is continuous, right? Because formally we want to show that not only our phi star or ni star maps SV onto SU, we also want to show that this is an isomorphism of Frichet spaces. So this lemma tells you that you shouldn't worry about continuity. If it's onto, then it's an isomorphism. So this is quite technical. And the third one will be that if we take any function on the real line that is C-infinity smooth, and we assume that this function is definable in some polynomially bounded omnivorous structure, then this function is tempered, which is to say that if you have a definable function, it can't explode too fast when it approaches the boundary. Okay, so these are the three lemmas. So, oh, something happened now. Okay. So the first and the second lemma hold for any open subset of Rn. So you don't assume anything about definability. So as said, the first lemma is quite technical to prove. You just need to cook this Schwartz function. And the second one, essentially, it's just the closed graph theorem that also holds for Frichet spaces. You have to show that the graph of ni star is closed, and it's not too difficult. So these two holds for arbitrary open subset. And the third lemma follows from Lewis-Savage inequality. So what you do, you look at the maximum of your function in an epsilon neighborhood of the boundary of your set U, and then you think about as you vary epsilon, you get a definable function, and then you see that Lewis-Savage inequality implies quite easily the bound we want. Okay, so just 1 second, I have something. Okay, yeah, okay, now I see it. Okay, good. So we have 1, 2, and 3, and they together imply quite easily our proposition. So what do we have to do? So I'm reminding you, we want to show that if phi is definable in a polynomially bounded omnivorous structure, then it induces an isomorphism of Schwartz spaces. So first of all, note that the second lemma tells us that it is enough to check that it pushes the Schwartz space to the Schwartz space, right? We don't have to be worried about continuity. And then we have a function that is S composed with phi that is written down here below. And this, hey Dima, and this S composed with phi, we need to check that it is Schwartz on the new space, right? And it is enough by 2 to check that it is Schwartz. Now, how do we do it? We just show that if we take any partial derivative of it and we extend it by 0, we get a continuous function. It's enough, right? To check that all derivative extends by 0. Now, how will the derivatives of S composed with phi will look like? It will be just some derivative of S evaluated at phi of x times some derivatives of phi, right? We will have sums of such things. We use the Leibniz rule and the chain rule, so we have many such creatures. But any derivative of S is Schwartz also, right? A derivative of a Schwartz function is Schwartz by definition almost, and all the the elements outside the derivatives of phi will be definable, right? Because derivatives of definable functions are definable. So, so we will have S composed with phi times partial derivatives. But partial derivatives are definable, and by lemma 3, they are tempered. So this product will be a product of Schwartz function and a tempered function. So it will be Schwartz again by lemma 1. Okay, so this is hand waving the proof. But these kinds of games show you that when we are working in a definable structure, in a definable setting, in a polynomially bounded environment, or in polynomially bounded structure, then this notion of rapidly decaying makes sense and everything works. So for instance, we can define Schwartz functions for abstract manifolds, right? Because these diffeomorphism will preserve the space. So this is the proposition I wanted to present in some details because it gives us kind of the taste of what's going on. So let's just list the other results and then go to the quasi-conformal setting. So, and I called it more implications of Lewis-Savage inequality because essentially all you have to do is do nothing special, and when you're stuck, you must use Lewis-Savage, and it shows you that everything is compatible. So, yeah, I need to, okay. So if we have a definable manifold in a polynomially bounded, and I'm stressing polynomially bounded minimal structure, and for instance, an open definable subset of Rn would be an easy example, then we have essentially that the whole theory works. So first of all, the assignment of the space of tempered functions will be a sheaf, which is to say that the notion of being tempered is a local thing. So if you have two subsets, you have a function that is tempered on one, you have a function on the union of two subsets such that it is tempered here and tempered there, then it is also tempered on the union. And well, it's not really a sheaf. You don't have a topology for a definable manifold, right? You have a restricted topology or a Grothendieck site or whatever. But essentially you have everything like a topology, but you only allow finite unions of open sets. So you have a kind of a topology. So in this setting, the assignment of the space of tempered function will be a sheaf, which is to say that the notion of tempered is local. The assignment of the space of Schwartz function will be a cosheaf, right? Because we said that if we extend the Schwartz function, we get a Schwartz function on the big space. So the direction is going to bigger and bigger spaces. Well, flabby is, it's like a flabby sheaf, but all error reversed, which means that the extension is injective. But if you have a cosheaf of functions, then the extension is almost always injective. Well, in any case, it's not very important. What is important is that the assignment of the space of tempered distributions is a flabby sheaf. Let me say a few words about this. So the space of tempered distributions is just the dual, the continuous dual to the Schwartz space. And in fact, often when people are talking about Schwartz functions, they are really worried. They really care about tempered distributions, and the Schwartz functions are just a tool to define them in a sense. So we have that distributions not only extend, but they extend, and this extension is, I'm sorry, not only restrict, but this restriction is onto. So if you have a small space and you have a tempered distribution on it, you can always extend it to some tempered distribution on the big space, because the restriction morphism is onto. This is the meaning of flabby. So, okay, so this works. The third property is kind of technical, but it's also important because, well, I will explain how it works, that any compactly supported function is Schwartz. So first, it's important because you expect it to be the case, right? Compactly supported functions are just zero as you approach the boundary, so they should be Schwartz. But moreover, it is important because if you're looking on a compact space, then any C infinity function is Schwartz. And this is important because if you care about C infinity functions, and some people care about C infinity functions, and you want to study them on compact spaces, then you can study Schwartz spaces of these spaces, and it will be the same. So sometimes it's more convenient. And the fourth property, oh, no, I have two more. So the fifth property will be, okay, and this will be especially important as a motivation, maybe for the second part of this talk, and maybe in general, that no matter how bad your space is, well, in this case, it's definable in a polynomially bounded or minimal structure, so it's not too bad. But in general, this holds for any open subset of Rn. You can always find a Schwarz function that is positive everywhere. So no matter how bad your boundary is, maybe your boundary is of Hausdorff dimension almost 2, and you live in R2, but still you can find a function that is positive everywhere. So your boundary, even if it's really bad, it can't force you to be identically 0 as you approach it. Okay, I'm saying following Whitney because there is a classical theorem by Whitney saying that any closed subset of Rn may be realized as the 0 locus of a C infinity function. So here we show something a bit stronger, but the proof is very similar. Well, there is something else to do, but in principle, the idea of the proof is the same, saying that any closed subset of Rn may be realized as the flat locus, as the place where a function is 0 with all its derivatives, and not of a C infinity function, but more of a Schwarz function. So you can also make sure it decays at infinity. Okay, so this is this statement, and the sixth statement will be just tempered partition of unity. So if we have a finite definable open cover, then you can always find enough tempered functions such that A, each function is supported in one of your patches, B, they all sum up to 1. Well, they're also non-negative, okay, and they all sum up to 1, and C, if you multiply one of these functions with any Schwarz function on the big space on M, you get a Schwarz function on the small space on this UI. And this is important, for instance, to show part 3. So, oh, I didn't say, so part 2, I'm sorry. So a sheaf of functions means that if you have a function that lives on the big space, it is tempered here and tempered there, it must be also tempered on the union. A cosheaf of functions mean that if you have a Schwarz function on the big space, it must be the sum of two functions, Schwarz functions, one lives here and one lives here. So this is the notion of a cosheaf of functions. It's not so important, but if you think about it, C gives you the proof, because if you give me a Schwarz function on your big space and you want me to show it or to present it as the sum of Schwarz functions on the small spaces, there you have it using this tempered partition of unity. Now I wrote in parentheses C also Fisher, because Fisher in fact has a theorem saying that you can always have, Andreas Fisher I should say, you always have definable tempered partition of unity, right? So, and we said that any definable function is tempered, so there's a proof of 6 in 3 words. When I wrote it, I wrote the proof, but which is easier than Fisher's proof, because I prove less, right? I'm only saying it's tempered. I'm not guaranteeing that it's definable. Okay, so this is a polynomially bounded or minimal case. What happens with non-polynomially bounded? Well, we have a nice theorem, right, by Miller, saying that if we have an O-minimal structure, by Chris Miller, I should say, right? There's more than one Miller. We have a polynomially bounded O-minimal. We have a O-minimal structure that is not polynomially bounded. Then the exponential, the global exponential from the real line to the real line is definable. So this immediately tells us that almost nothing works in this case, right? Because in any O-minimal structure that is not polynomially bounded, we will have the example that we already seen, right? So we've seen this example, and this example tells you that you cannot even say what is a Schwarz function, because these two pictures are the same manifold in for instance, Rx. These are just two coordinate systems, and you see that the notion of being Schwarz is not consistent. In fact, it's even worse. Even if you fix your embedding space, say you are walking in Rn, and now you think about definable open subsets in Rn. So forget abstract manifolds because it doesn't work. Even then, many things will not work. For instance, there is a very concrete example showing there is no tempered partition of unity in this case. Namely, if you allow me to use only polynomials and exponential, which is something you are always allowed to do in non-polynomially bounded omnimer structures, we can take, and this is a very easy example, it lives in R2. We can find two open subsets and a function that is tempered here and tempered there, but a function that is defined under union, it is tempered here and tempered there, but it is not tempered globally. So as long as I'm allowed to use the exponential, nothing works. Okay, so this is all I wanted to say about this theory in the ominimal case. Are there any questions before I proceed to the next part? No. Okay, good. So we will get to quasi-conformal geometry in a few minutes, but let's build it. So everything I'm about to say from now on is based on my joint work with Eden. So let's try to understand together which other diffeomorphism induce Schwartz equivalence. So we've seen that definable diffeomorphisms in polynomially bounded omnimer structures induce diffeomorphisms. So this is the main problem we want to address. So we have a C-infinity smooth diffeomorphism, under which conditions it induces an isomorphism of Riche spaces. So the first step is really easy. We know by the lemma we had before that we only need to check that this diffeomorphism pulls and pushes Schwartz functions to Schwartz functions, right? We're not worried about continuity of this operation, of this map, right? So this is the first step. Okay. So we fixed the Schwartz function on V, and we want to show that if we precompose it with phi, we get a Schwartz function on U. And we'll do everything symmetrically, right? So everything, we'll later change the names and think about phi minus 1 and from V to U. So it will make assumptions on both V and U together. So recall our proposition we had in the beginning. In the beginning, if we have a Schwartz function on the big space on Rn that is identically 0 on outside some set, then in order to show that this function is Schwartz on this set, it is enough to show that if you divide it by the distance to the boundary function to high powers, you get something that is bounded. So let's just keep this in the next slide. So we have a function on V, and we want to show that it is Schwartz on U. So we know by the proposition that we have the supremum on V of our function S divided by the distance to high powers. This is finite, so this quantity is bounded. And we want to show the same thing for S composed with phi on U, right? This is what we need to do. So if by any chance our phi distorts the distance to the boundary polynomially, and what do I mean by this? I mean that we can find two positive numbers such that the distance of phi of x to the boundary of V is comparable to the distance of x to the boundary of U. So I'm allowing constants in all kinds of places, right? So polynomially, so maybe we need to take high or low powers of this distance. And maybe we have some big constants, but we don't care. So these are good news. Why these are good news? Because we look at the supremum. Do you see my pointer? Can you see my pointer here? Yeah, okay, great. So we need to show that this supremum is finite. What do? We use this inequality to change the denominator, and then we get something that is very similar to this bound we already have, right? So these are good news. And what kinds of functions phi only distorts the distance to the boundary polynomially? For instance, Helder maps. So if we have any Helder map actually from U to V, then we can show that it has this boundary, this distance to the boundary distortion property. And I write by Helder because, as I said, we want to do this thing for Schwartz function on V to show that this is being pulled to a Schwartz function on U, and we also want to do the other side, right? So if we assume that our phi is Bihelder, then we are in good shape. So we can show that the bound for 2 of the proposition holds. Now we are not done yet, right? Because we said that we need to show 2, and we also need to show that our function extends by 0 to a Schwartz function on Rn, right? So how do we show that our function extends by 0 to a Schwartz function on Rn? First of all, let's assume that, okay, so yeah, so we still need to show that S composed with phi extends by 0 to a Schwartz function on Rn. So first, let's assume that U is bounded, and V. So if everything is bounded, then being Schwartz is like being C infinity function, right? So now we need to show that if we take S composed with phi, and we extend it by 0, we get something that is C infinity smooth. So what we will do, we will show that all the partial derivatives of S composed with phi extend by 0 to a continuous function. This is enough, right? So now let's go to the n equals 2 case. So think about R2 or think about the complex plane. But again, I want to stress when we're thinking about the complex plane, it's just because it's convenient to work in this notation. We're still thinking about real valued functions. So if n equals 2, V and U are bounded, and phi happens to be a conformal map, then we can have a nice bound. Let's see this bound. This will be the ugliest formula I will write. So if we look at the kth derivative of phi, now I'm sweeping some stuff under the rug, right? Because here k is a natural number, right? So when I write phi k, I mean d to the z to the power k. I'm taking derivatives of phi as a complex function from C, right? That lives on the complex plane. So we can take derivatives of, it's a function from R2 to R2 or from C to C. So this is the d to the z derivative if you want. But since, and when we are talking about Schwartz functions originally, we're talking about derivatives in the x direction and one direction, right? And now we're moving to talk about d to the z and d to the z bar. But since phi is conformal, then d to the z controls this d to the x and d to the y. Actually, it's the same up to some constant, I or something. And d to the z bar would be just 0. So in any case, there's some technicality to verify, but everything is okay. You can believe me, it's okay. So let's look at this derivative. So this derivative, we have a formula, right? A Cauchy's integration formula, which says that, so I just wrote it down. This is the first equivalence, the first equality. So we just integrate along a closed curve containing this point z. And what is the closed curve? We take gamma to be a circle centered at z of radius, the distance of d to the boundary over 2. 1/2 of this thing. So this phi lives inside U, right? Because the distance to the boundary is something, and we take a circle that is smaller than this thing, right? So everything is okay. We can take this integration. And okay, so I just wrote the formula. So the first inequality is just putting absolute values everywhere. And then we have an equality saying that, okay, what is W minus Z in this expression? It's just the distance, it's just the radius of gamma, right? W minus Z, the absolute value is just the radius of Z for any point in gamma. So this is distance of Z to the boundary over 2. So I just plug it in here and we get this equality. And the last bound follows from the fact that V is bounded, right? So if V is bounded and phi is a map that maps U onto V, then this phi of W is bounded by something, by the diameter of V. Well, if it contains 0. So, but it's bounded by something. So in any case, we have that the kth derivative of Z is bounded by some constant over the distance to the boundary function to the power k. Maybe k is very big, but I don't care. In fact, it's not big. K is exactly the case derivative here. So if we look at the first derivative, it does not explode more than 1 over to the distance to the boundary. But in any case, we have this bound, and now we are pretty much done. So in this case, all the partial derivatives of S composed with phi goes to 0 as Z approaches the boundary. Why? Because the partial derivatives of this thing will be something of the form some derivative of f evaluated at phi times inner derivatives, times these derivatives of phi. But you can see that these derivatives of phi only explode as 1 over some polynomial to the distance to the boundary, and the first element of some derivative of s evaluated at phi is Schwartz, so it decays faster than 1 over to the distance. All right, so this is, we'll have a Schwartz function multiplied by something that explodes, but not too bad. Okay, so we have that S composed with phi extends to a C infinity function and hence to a Schwartz function. So we kind of proved the following theorem. So if we have phi from U to V that is a conformal Bi-Helder map between bounded domains in C, right? So we said conformal, we said bounded, we said Bi-Helder, then it induces an isomorphism of Riche spaces. So we kind of proved it up to me cheating and sweeping things under the rug. And then we have a nice corollary saying that any two bounded quasi-disks are Schwartz equivalent. Now, I didn't tell you what's a quasi-disk. I will tell you in a minute. But let me give you an example. So for instance, if we look at Koch snowflakes, so we have we start with an equilateral triangle, and then we construct equilateral triangles on the 1/3 segments in every side, and we keep on doing it. But in every step, we take 1/3. So the angle is fixed in this iteration. So this snowflake defines a bounded open domain in the complex plane, right? The interior of this thing, right? This snowflake is a Jordan curve, so you have the bounded component and the unbounded. So the bounded component will be a quasi-disk, a bounded quasi-disk. So in particular, we proved that the interior of Koch snowflake is Schwartz equivalent to the unit disk, because the unit disk is also a quasi-disk. And this example is interesting, first because it's nice, and second because this snowflake is not definable in any, well, O minima structure, not to mention polynomially bounded, right? So it's not definable in any O minima structure. So this is a nice example. So now let me give you the example of a quasi-disk and a quasi-circle and a quasi-arc, but I need to stress that this will be a very, very brief review. So there's a lot of interesting mathematics behind it. In particular, I will not say quasi-conformal at any point, but you may ask, why is it called quasi-circle? So the answer is, it's an image of the circle under a quasi-conformal map or under a quasi-symmetry. So on the complex plane, quasi-conformal maps and quasi-symmetries are almost the same. But in general, you can say a lot of interesting stuff that I will not say, but I will give just the essential definitions. So what is a quasi-circle? So a quasi-circle is a closed subset of the complex plane. Such that if you look at its closure in the Riemann sphere, then this is a Jordan curve. And moreover, if you take any 2 points on your G0, on your quasi-circle, and you look at their distance, it controls from above the diameter of the connected component of J0, so of the smallest connected component. So how do you explain it? So you have your quasi-circle, you take out 2 points. So you can look at the smallest connected component that connects these 2 points. Maybe there's more than one, maybe there's 2, so take the smallest. So this diameter should be bounded by the distance of these 2 points, up to some big constants, but okay, but some constant. I think maybe in the literature, sometimes it's denoted K, this C, right? And then it's called, yeah, I think, and then it's called the K quasi-disk. But okay, but this is a quasi-disk for us. And so this is a quasi, I'm sorry, this is a quasi circle. What is a quasi-arc? A quasi-arc is a subset of some quasi-circle such that its closure inside the Riemann sphere is homomorphic to 0, 1. Note that this subset doesn't have to be connected. So for instance, if you look at two infinite rays that have a hole in the middle, so in the Riemann sphere, it's just, you know, these two ends connect, and then this is a nice quasi-arc. And the third definition would be what is a quasi-disk? So a quasi-disk is a simply connected open subset of the complex plane that its boundary is a quasi-circle. Okay, now these definitions, you may not like them. So sometimes people work in the Riemann sphere, and then you don't need to think about the difference between bounded, unbounded, simply connected, not simply connected, the closure in there. So you just think about stuff that live in the Riemann sphere. However, we're used to think of Schwartz functions on Rn, in particular on R2, so we prefer the approach on just work in the complex plane, but it's a matter of taste and everything is equivalent, of course. Okay, so let me give you some examples. So the upper half plane is a quasi-disk, right? It's the boundary is just the real line. The real line is a nice quasi-circle. However, an infinite open strip is not a quasi-disk. Why? Because if you look at the closure of the infinite open strip, so these are two parallel lines, at infinity they meet. So it's not a Jordan curve, right? It splits the Riemann sphere into 3 connected components, so not 2. So it's not a quasi-disk, and this is an important example because it is definable in any polynomially bounded or minimal structure, right? So we know that this infinite open strip, for instance, is Schwarz equivalent to the unit disk because this infinite open strip is Nash diffeomorphic to, or semi-algebraic diffeomorphic to the unit disk, to the unit disk, yeah. So, but it is not a quasi-disk. So this is an example to show you that neither the two approaches is strictly stronger than the other. I mean, we have definable stuff that are not quasi-disk, and we have quasi-disks that are not definable. There's another example. If you take a cusp, an algebraic or exponential, it's never a quasi-circle. So an algebraic cusp would be just the 0 set of x squared equals y cubed. So this is again definable in any reasonable, in any minimal structure, but it is not a quasi-circle. And in fact, this too hints for a big, I don't know, classification theorem or equivalent definition of Alford, saying that if you have a topological circle, it is a quasi-circle if and only if it has no 0 angle cusps. Okay, I didn't define everything properly, so this is like, but this is the motivation, the intuition behind it. This is an interesting example. If you take the real graph of a sinus, so take just sinus x, I have something, 5 minutes. Okay, I'll try. So if you take this thing, this is a quasi-circle because at infinity it's nice. But if you take this thing that a sinus that is oscillating faster and faster, so you take the sinus of x squared, of the real part squared, this is not a quasi-circle. And this is a very interesting example. Okay, so these are quasi-disk and quasi-circle. Let me very quickly tell you some more results without details. So what are the diffeomorphism-induced Schwartz equivalence other than these Beihelder, conformal, and definable? So we can show that if you have a Mobius transformation that maps U onto V, it's also it induces Schwartz equivalence. And then we have a corollary that any two quasi-disks in general are Schwartz equivalent. And why is it true? Because if you take an unbounded quasi-disk, you just take a Mobius transformation that turns it into a bounded quasi-disk. And it is well known that Mobius transformation are maps quasi-disk to quasi-disks, again, because they are quasi-conformal on the sphere. Another example, which is very nice, this is Eden's favorite, I think. So if you take two open simply connected domains that do not contain 0, and we take any holomorphic square root, any branch of the square root function, then it also induces Schwarz equivalence. And note that these two lemmas are very similar to being definable, right? Because Mobius transformation is kind of definable, but not really, because you don't know that your U and V are definable. So you are given a formula that is definable, but it lives on a set that is very bad. So yeah, and also the second lemma, so you have a square root, so it's a formula, but you don't know how the formula changes. So, and quasi-disk and these U and V here can be really bad, can be like infinite spirals and bad things. Okay, and this lemma gives us another theorem about what happens if you take the entire plane and take out the quasi-arc, but let's skip it because I want to take 2 minutes to talk about Kobe's theorem, which is really nice. So Kobe's theorem is not ours, unfortunately. So we tell you that if you have a domain in the complex plane that have, well, finitely many or countably many connected components in its boundary, then it is conformally equivalent to what people call a circle domain, which is a domain such that the boundaries components are only points and circles. So this is true for finitely many connected components in the boundary, proven by Kobe when he made the conjecture that it should be true for any subset, for any domain. And by Heshram, it was proven for countably many. And note that, okay, nothing works. Okay, that this theorem is a generalization of the Riemann's mapping theorem, right? Because if you have a simply connected domain, and it's so it must be conformally equivalent to a disk, right? And in particular to the unit disk. But note that in contrast with Riemann's mapping theorem, here the fundamental group does not completely determine the surface, the domain. Let me skip on this, but just tell you our theorem. So if we take a domain whose boundary connected components consists of at most countably many points and finitely many quasi-circles, so we cut out many Koch snowflakes, for instance, and we also allow one quasi-circle that is unbounded. So we take the complex plane, we cut out five Koch snowflakes and a few other rectangles, and we also take out the entire half plane, then this is Schwarz equivalent to a circle domain. And the proof of this theorem is essentially saying, okay, let's take the map that Kobe gives us, and let's show that it extends to a quasi-symmetry on the complex plane, and this is enough to be by Helder, and this is enough to give us everything we want. So in the last minute, I will tell you what are the open questions. So we still don't know, is it true that any two C-infinity diffeomorphic subsets of Rn are Schwarz equivalent, right? So I told you in many, many cases where you have Schwarz equivalence, I showed you the exponential map that doesn't induce Schwarz equivalence, but a minute after I showed you why these sets are Schwarz equivalent. So it's not clear whether any two C-infinity diffeomorphic subsets are Schwarz equivalent. And there you have two examples. So if you take this, the complex plane, and you cut out the infinite, the faster and faster oscillating sinus, if you cut it out, we don't know if it's diffeomorphic to the unit disk. We know that if you cut out just the sinus, it is diffeomorphic because it is a quasi-arc. But if you take something that goes faster and faster, we don't know. And the second example, and it will be the last example, so if we take the 0-1 interval, we delete the 1/3 counter set, we get an open subset. It's quite bad, but it's an open subset. And it consists of countably many intervals. So the question is it Schwarz equivalent to just a union of intervals far away from each other? So we don't know this question too. If I would have to guess, maybe I would say that, yeah, I made a guess once and then I turned out to be wrong. But if I would have to guess, I would say that the second example should be true. Somehow we should be able to cheat and construct a Schwarz equivalent. Okay, so thank you. So if you want to read more, the first reference is to the thing about definable stuff, and the second is the preprint of Eden and myself. And since you told me 5 minutes ago, so I can take 30 extra seconds and just tell you that there you have another example of application of Koch snowflake. If you have a 5-year-old that is really into Frozen, and he likes Anna and Elsa and all these snowflakes, then you can show him how to construct this thing. So you see, there's my son. He's dressed up like Elsa. And he saw me preparing these slides in the weekend, and he asked me, what is this snowflake? So I showed him how to construct. So on the right-hand side, you can see him trying to, yeah. So we stopped after 3 iterations, I think. Going infinitely many, it will be too difficult. Okay, yeah, thank you.